All right. Atomic structure 8, we're dealing with the octet rule. And right there you see oct, O-C-T, oct like October. October used to be the 8th month over 2,000 years ago under the Romans, right? The Romans started the year in March. We're going way back. We're going to the time of Scipio Africanus, who defeated Hannibal about 30 years after his death. They changed it. They made January the first month, but March used to be the first month, and so October used to be the 8th month, and it's not anymore, but we still have the prefix oct, meaning 8. Anyway, let's deal with the octet rule in chemistry and atoms. So in simple terms, like elements, atoms, they want to be noble. They want to be like the noble gases, and I'll explain that in a minute. So they want to be complete. That they want to have a tendency, there's a tendency in the atoms to have 8 electrons in their valence shell. So let me get a clean page going. And here's a picture of helium. Let's get the pen. Why don't we start with red? So I did mention that atoms, and we'll get a little blurry here, right? Let's fix that. They want, I will personify them today, they want to have 8 electrons in their valence shell. So let me explain valence shell. So the valence shell, the little arrow there, is the last shell. It's the last shell. It's the last ring. It's the last orbit you may hear. It's the last cloud. It's the last energy level. So, and so this is a Bohr model of helium. He is helium. So I'll write it here, helium. Now, it doesn't work for helium because helium only has one energy level that we see here. It has one ring, one shell. So in the first shell, you can only have up to 2, and helium has it already. So that's why helium is complete. Helium is a noble gas. And they call them noble gases because, in a way, they don't want to mix with the commoners, the common elements. That's why they termed it that way, because they're complete. Noble gases won't react. They don't want to react to form compounds. They're complete. So here's helium. It's complete. It has its 2 electrons. And let me just try to make you understand something. Electrons aren't really balls. They're not orbiting the nucleus, and I've been saying this in other videos also. So when we say balls, we mean particles. They're more like waves. But for teaching purposes, we'll just stick with it right here. So just again, atoms want to usually have 8 electrons in their valence shell. And there's a what if here. There's a little more to this, and I'll get to it in a minute, except for, of course, helium, because it only has one shell. So here's lithium. Now, lithium has 2 rings, 2 orbits. Let's get our pen. Let's change it now. Let's change the color to blue. So lithium right over here, and lithium is an alkali. It's an alkali metal. It has 2 rings. You see the 2 rings, or the 2 orbits, if you want to call it, or 2 clouds, some people will say, or 2 energy levels. It has 2. And so in the first energy level, which we call the K, it has 2. And you see this right here, I'll circle it. It says S. So I have to explain that. When we're dealing with the octet rule, we're only going to deal with S and another one called P, which I'll explain in a minute. So in each energy level, except for the K, you can also have these sub-levels, and they're also called suborbits. So they're like shells within shells. So, and this will be the L level. So let's say we have a ring here, right? This is the K. And the K can only hold the S-type electrons. Only hold the S. And the S-type can only have up to 2, no matter where there is an S. So you see this blue, lithium has 2 in its first shell, and you can't have any other electrons in the first shell, so it's complete there. But in the second shell, it has one s. It can hold one more if another shows up, but it only has one. So remember, always when you see an s, there's only two, up to two. So in this other level here, let's say this other level, we call it the L level, you can have s's and you can also have p's. So there are these subshells within shells. And the p can hold up to 6. So if you add 6 plus 2, you'll get that 8. Now, let's go back to make sure we understand. The valence shell, this is the valence shell. The last shell is the valence. Last ring, the last orbit, whatever you want to call it. That's the valence shell. And the electrons in the valence shell are called valence electrons. Makes sense. So in the second shell, the L shell, you can have up to 8. You can have up to 8. 2 will be S and 6 will be P. All right, and there's other subshells, right? We're going to talk about the S, there's the P, and there's more. So let's look at more elements. All right, so here you see beryllium. Notice about beryllium. So let's use purple. So here we have the K shell, the K ring, the L ring, the L orbit, whatever you want to call them. And again, there are suborbits. So you see in the K, it has its 2 S's, and it has 2 S's in the second shell. So the S's are complete, but atoms want to have 8 of S and P. So the P, as you see right over here, there's the P, you can have up to 6. So the S again, up to 2 only, up to 6. And then there's a D, which we haven't seen yet. That's up to 10. And then there's the F, up to 14. So when we're dealing about the octet rule, we only are concerned with S and P. Just remember that, just the S and P energy subshells. So beryllium doesn't have any P's, it just has the S. But remember I said S is only up to 2. So look at boron. This is boron over here. Boring. No, I'm kidding. So boron finally gets another P. It gets 1 P. So it has its 2 S's, 2 sub S's, and now it's P. It could hold, now how many more P's can fit in boron? How many do you think? 7 more or 6 more? Or 5 more? What do you think? Well, remember, look over here. P can be up to 6. You already have 1, so you can put 5 more. So boron's looking to either gain 5 more to be complete. 5 more of the P. Let's keep going. You'll understand this. So now we have carbon and nitrogen. Guess which one's nitrogen? Yeah, you know. So look at carbon here. So on the first shell, the first orbit, it has its 2 S's. And remember, let's get our pen working, by the way. Let's use green. Remember, it can only have 2 S's, up to 2. And the first shell can only have 2 S's only. No P's, no D's, no F's. So up to 2. What about the P? You remember that? Up to what? Up to 6. So how many does carbon have? It has 2. It needs 4 more to be complete. And look at nitrogen. It has 3. It needs 3 more to be complete. So again, when we're dealing about the octet rule, it's only the S and P subshells we're dealing with. So let's keep going. Now we skip to fluorine. Now fluorine is the most reactive element on the periodic table. It's very reactive, not radioactive, but reactive. In other words, it will react to other elements better than anything else. And it is a halogen. So we'll write up, we'll make sure our pen's working first of all. We'll use that color, why not? So fluorine is a halogen. And halogens are very reactive. They want to react. They want to mingle. Look at fluorine. It has its 2 S's. First shell is complete. And in the second shell, let's count. It has its 2 S's. And look at the P's now. It has 1, 2, 3, 4, 5. It needs 1 more. That's why fluorine is very reactive. It just needs 1 more to become, look over here, right there, that's neon. Neon is a noble gas like helium. It's complete. Why is it complete? It has its 2 S's in the first shell. In the second shell, it has its 2, and it has its 6 P's. 1, 2, 3, 4, 5, 6. It is complete. Noble gases don't react. They will not form compounds. That's why they're noble. That's why they called them that way back in the 1800s. They're noble gases. They will not react. So, in a sense, we can say that all elements are trying to be noble. They're trying to be complete. That's the octet rule. Let's keep going. Now we have sodium, Na, and chlorine. And you know, when you put these together, what do you think they make? Sodium chloride. And what is that? And that's table salt. That's table salt. So sodium, this is sodium over here, and this is chlorine. One's a gas, chlorine's a gas, and sodium is a metal. Sodium is an alkali. Alkalis are very reactive, and chlorine is a halogen. And halogens, like I said, are very reactive. Let's look at sodium. So it has its 2, as we said, in the K level. This is the K, this is the L, this is the M. So if we look at the L shell, it's complete. It has its 6 P's and its 2 S's, but it doesn't have any P's in the M level. So there's no P's. It just has 1. So what sodium is trying to do to be complete, it could just get rid of it. If it gets rid of this electron leaves, then it'll be complete. It'll be noble. Of course, it'll change, but you're getting the sense if this leaves. So in a sense, alkalis are trying to get rid of electrons, where halogens are trying to gain. Look at the halogens here. Let's count the P's. Again, this is the K, L, M. We have 1, 2, 3, 4, 5. It needs one more P, and then it'll have a total of 8 in its valence shell. So chlorine's trying to gain an electron, where sodium's trying to lose it. So it's a perfect match. When they come together, chlorine will take sodium's electron, sodium will lose its electron, they will make a compound, which is table salt, which we need to survive. By the way, and I had other videos on this, the halogens are electronegative. In other words, they want an electron. And the most electronegative is fluorine, which we talked about. It's the most reactive. The alkalis are also very reactive, but they're electropositive because they're losing an electron. All right, so here we have arsenic. Arsenic and lace, a movie, right? Look at arsenic. So now you see the D subshell appear. But we don't care about the D subshell when we're talking about the octet rule. So let's use purple. Why not? So let's look. We have its 2 in the K. Remember, this is the K, the L, the M, the N orbits. And these are the subshells or the suborbits. And S is up to 2. What's P? You remember. Up to 6. And D's up to 10. By the way, there's also F, which is up to 14. And you may see a pattern. What's happening each time? You know the pattern? So look, it's going up by 4 each time. It's going up by 4. There's our pattern. So arsenic has its D, so it has its 2 S's in the first shell. It has its 2 in the second. It has its 2 in the third. It has its 2 in the fourth. It can only have 2. S's is always 2. And we look at P. P is always 6. So here we have 1, 2, 3, 4, 5, 6. And here's the P again. 1, 2, 3, 4, 5, 6. And here's the P again. 1, 2, 3. So arsenic only has 3 P's. It wants 3 more to be complete. Again, only the S and P's we're talking about. All right, now we have lead. All right, so it has that Latin PB, plumbum. All right, it's a Latin word. Actually meant black lead, because the Romans used to think that tin and lead were the same They called lead black lead and tin was white lead. But now here you see this purple one over here. Let's get the pen going. We'll use black. Why not? So you see that color right there? That's the F. So again, up to 2. You know this by now. Up to 6. Up to 10. Excellent. And F up to 14. So let's look. Let's look at this valence shell. The valence shell is the last shell. It has its 2 S's. And let's see, what about the P's? 1, 2, and we're missing one on the bottom here. We're missing one on the bottom. Let me get a better picture. Well, no, actually, no, we're not missing one. Let's make sure we have the right levels here. Let's double check. Remember, we have the K. Let's get our pen working first of all. We'll get to that one in a minute. All right, let's get that pen working here, black. Make sure we have our... You can notice how the atom's getting bigger and bigger and more unstable. So we have our K, we have our L, we have our M, we have our N, our O, we have our P, getting very big. So in the O, in that O level, we have 1, 2, 3, 4, 5, 6. So it's complete. It's complete. But on the valence shell, here's the valence shell, it only has 1, 2. So it needs 4 more. Lead needs 4 more to be complete. And here's astatine. So let's count astatine. Here's a little test. Where is the valence? Where are the valence electrons? Right, the last shell. So it has its S, it has its P suborbital, D suborbital, and it has its F suborbital. So how many does it have in its valence electron? Let's count. 1, 2, 3, 4, 5. It wants 1 more. 1 more and it's complete. So again, just to review, the octet rule is where there's a tendency for atoms to want to have 8 electrons in their valence shell, their last shell. And those electrons are in the S subshell, suborbital, or the P, not the D, not the F, just the S and the P. So here, right here, we have our pen working. We'll go back to red. These are the alkalis. They're very reactive. They want to lose an electron because they're electropositive. And the halogens over here are very reactive also. They want to gain one. And we did say fluorine over here is the most reactive. As you think reactivity, it goes up in the halogens. It goes up that way, but in the alkalis, it goes down. So francium right over here, which is not only reactive, it's also radioactive. It's the most reactive alkali, and fluorine is the most reactive halogen. All right, that's our video today. Oh, and just to make sure, so remember, in each shell, like a K shell, an L shell, there are subshells. Just to keep that in mind. All right.